Today also we'll continue with the basics. So just note down the shapes of orbitals. Shapes of orbitals. So every one of you are aware of the shapes of orbitals. S-orbital, so any of these three you can just draw for an s orbital. Center will be the nucleus. Around the nucleus there will be s electron density. As you move away from the nucleus, the probability of finding the electron will decrease. So around the nucleus we have to draw the electron density to be little higher. As you move away from the nucleus, the electron density should be drawn little lesser. Okay, that you call it as a contour plots, contour diagrams, or simply you can put all plus. It means it is all same phase, or it could be complete minus. So either you have to put completely plus or you have to put completely minus. Okay, that is s orbital. And what is the shape of s orbital? Spherical. So the shape is spherical. You can note it. Now here I'll just introduce another important point. We are aware that symmetry elements, there is an element called as inversion. Okay, what is this inversion? Suppose I take any object, right? I'm taking any object. From the center, if I draw a line that meets a point, and if I extend the same line in the opposite direction to the same distance, if it meets an identical point, then I say inversion is present in it. Okay, so whatever I may take, starting from the center in the sense, it is the center of gravity. Starting from the center, if I draw a line which meets a point, if I extend the line in the opposite direction to the same distance, and if it meets the identical point, then I say inversion is present. Okay, so just imagine I have a pen. Imagine that this is cylindrical. Don't go with this point. Just imagine that it is like a cylinder. Now starting from the center, if I draw a line, it is meeting a point. If I extend the line in the opposite direction to the same distance, it is meeting an identical point. Then I say inversion is present in it. Okay. In the board, do you have inversion? Yes, there is an inversion because you have to just take it as a rectangle. Don't take all the colors or whatever designs that are present. Just imagine it to be a rectangle. So if it is a rectangle starting from the center, if I draw a line, it is meeting some point. Maybe from the center, if it is meeting this point, if I extend this line in the opposite direction to the same distance, it is meeting an identical point. Then I say inversion is present on the board, or inversion is present in the board. Okay. Now look at the s orbital. For s orbital, do we have inversion? Starting from the center, this is the center. Okay, nucleus is present. From that nucleus, I am just drawing a line. It is meeting a point which is plus phase. In the opposite direction to the same distance, it has to meet an identical point. So is it a plus phase? Yes, everywhere it is plus. Starting from the center, I am drawing a line. It is meeting plus. Opposite direction, same distance, meeting plus. Starting from the center, opposite directions, is it meeting plus? Yes. Or if I take minus, everywhere it will meet minus. So I say inversion is present in s orbital. If inversion is present in s orbital, parity, we say it is even. Parity is even in the sense, just imagine yourself in an s orbital. If you are imagining yourself in s orbital, wherever you go, what phase will you meet, plus or minus? Everywhere you will meet plus only. If it is plus, everywhere you will meet plus. Suppose if it is minus, wherever you go within the s orbital, you will meet minus only. It means parity is even. Everywhere it is like plus only, or everywhere it is like minus only. Okay, so wherever inversion is present, we say parity is even. And whenever parity is even, there is a symbol given. What is that symbol? Gerede. You give gerede symbol G. If parity is uneven, suppose if I meet plus in the opposite direction to the same distance, if I meet minus, then I say parity is uneven. Parity is uneven. If it is uneven, the symbol that I give is ungerede, U. So we have two symbols, gerede and ungerede. Gerede is given whenever parity is even. Ungerede is given whenever parity is uneven. Okay, so just note down. First, for S orbital you complete. Is inversion present in S orbital? Yes. If inversion is present, parity will be even. If parity is even, the symbol given will be gerede. Gerede is abbreviated as G. Simply we have to write it as G. In foreign universities they pronounce it as gerede. Not all foreign universities, some foreign universities they pronounce it as gerede. We pronounce it as gerede. So pronunciation is different. Gerede is indicated by small g. Parity is even, therefore we indicate it by small g. P-orbitals, directly I am drawing the P-orbitals, not the contour plots. For every orbital you can go for the contour plots. What axis is this? By convention we have taken it as Z. This is Y and X is pointing towards you. This is just a convention. Okay. In the center there is a nucleus. Now starting from the center, if I draw a line, if it meets plus in the opposite direction to the same distance, is it meeting plus? No. So inversion is present? Absent. Inversion is absent for p orbitals. If inversion is absent, parity is uneven. If it is uneven, the symbol is U. U for ungerede. Or it is pronounced some universities as ungerede. Un means 1. Okay, un means 1. Suppose if there are 11 carbons, what do you call it as? In your IUPAC nomenclature, if there are 11 carbons, you call it as undec. But un generally we pronounce, in foreign countries they pronounce it as un. Okay, they pronounce it as un. If it is 21, if it is 21, ecos. Ecos. Completed? It is not ecos, it is hen icos. Only for 21 we use hen, for 11 you use later on you can use hen. Suppose if 30 is triacont, what is 31? Hen triacont or hen triacont. Later we use hen, not un. And what is the shape of p orbital? P orbital is dumbbell shape. Every time you remember, in the center there has to be a nucleus. Okay, since there should be a nucleus in the center, how should you draw the lobes? Generally we have to draw two lobes like separated lobes. Usually what we do is we draw it like 8. Suppose that if I am drawing it like 8, Maybe it is passing through the nucleus. That is what it gives the sense. But it is, the electron density is not passing through the nucleus. It is either above the nucleus or below the nucleus. It can't be in the nucleus because it is a nodal plane. So to show that there is a nodal plane, there is no electron density at the nodal plane, we draw two lobes separately at a higher level. But at a lower level we simply write it like a 8. It is not actually like a 8. This is about p orbital. I said conventional axis. What do you mean by it? Conventionally this is taken as z, x, y. Suppose I want to take this as z. Can I take it? If you go to lower level textbooks, even in some degree textbooks, suppose if there are two pz orbitals are combining to form a sigma bond, then you are given as pz and pz combining to give you sigma. But if you find some other text, px and px will form sigma bond. In textbooks you can see px and px is forming sigma, py, pz are going for pi. So which one is correct? Is px going for sigma or pz going for sigma? Which one is correct? Both are correct. It is just a convention. I'll give you a simplest example. I think almost every one of you have completed your masters except one or two. You might have gone for an analytical balance weighing. In the analytical balance, where do you put the variables and where do you put the constants? There is a variable, there is a constant, right? So to which side will you put the variable, to which side will you put the constant? I'll ask you to weigh 1 gram magnesium sulfate. Where will you put 1 gram weight? Where will you start adding the magnesium sulfate? To which side? Magnesium sulfate, right side, because it is a variable. Where do I put the weight 1 gram? Towards my left hand side because it is like a constant. But that is just a convention. In some colleges it is almost said like a rule. You have to put the weight to the left hand side and the variable to the right hand side. It is just a what do you call convention. It is not a rule. Okay. Suppose that I am a left-hander. I am a left-hander. So which hand is convenient for me? Left hand, obviously. So where should I put the weight? I can put it to my right. Then I will be adding the magnesium sulfate from my left because this is my convenient hand. So all those things we call them as conventions. Or here let me give you another simple example. You are filling the burette. Two types of solutions can be filled, colorless and colored solutions. For colorless solution, which meniscus will you follow? Upper or lower? Lower meniscus. For colored solution, upper meniscus. Why do you follow upper for colored? Reason? Why do you follow upper for color, lower for colorless? Any reason for it? Suppose that I am taking a burette. There is a upper meniscus and lower meniscus. For colored we follow this. For colorless we follow this. Because for colored you can't see lower meniscus. It is colored solution, I can't see lower, therefore I follow upper. But for colorless I can see both. I can follow anything. Either I can go with upper or I can also go with lower, no issues at all. But since I am following upper for colored, I follow lower for colorless. It is a convention. Even for colorless, if I follow upper, for every titration you have to follow upper only. Got it? Lower, not just for colorless. Suppose you have taken a colored solution. Still you are able to see lower meniscus. You can follow lower meniscus. Absolutely fine. So it is not a rule. Remember, these are called as conventions. Okay? Simply they are called as conventions. One more convention I will tell you. Plus above, minus below. Plus above, minus below, every time we draw the same. Can I invert it? Can I put minus below and plus above? Yes or no? It is obvious. Plus and minus, I can also invert it. But why do we by convention take plus above? Because if it is just a wave, in that wave, it will be moving like this. So from the center, whichever is above, we put plus, whichever is below, we put minus. So as it goes above, we give plus, as it comes below, we give minus. That is why above we give plus, below we give minus. You can also invert it, absolutely no problem. Okay, next d-orbitals. How many d-orbitals? 5. Can you draw the d-orbitals? Shape, double dumbbell, suddenly what do you see here? Six orbitals. Here what I am doing is, consider this as Z, this is Y. Okay, just a minute, after I draw you can continue. X is towards you. This is along Z axis and this is Y axis, this is X axis. This is dz square minus y square, this is dz square minus x square. Okay, so these two combine to give you dz square. These two combine to give you dz square. So whenever we draw dz square, how do you draw the lobes in comparison with the other d orbitals? In comparison with other d orbitals, this lobe will be large along the z axis, and along x and y you will be putting a donut shaped structure, circular structure. So this is actually plus 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 plus, it is adding, therefore these two lobes will be large. In xy plane how many lobes are present? 1 2 3 4, 4 lobes. These 4 lobes are included in this circle. So if this is plus and plus, all this will be minus. Okay, so this is dz square. But actually how many d orbitals are there means we say only 5, but dz square is a combination of dz square minus x square and dz square minus y square. Look at d orbital, do you have inversion in it? Do you have inversion? All this is plus, all this is plus, this one is minus, everywhere you go it will be minus. So at the center there is a nucleus, in the center there is a nucleus. What happened? Right, starting from the center if I draw a line, is it meeting plus? In the opposite direction to the same distance also it is meeting plus. Starting from the center if I draw a line, it is meeting minus. Opposite direction to the same distance also it is meeting a minus point. So I say inversion is present, parity is even, gerede. You choose any d orbital, it will be gerede. Let it be dz square minus x square, dz square minus y square, any d orbital it will be gerede. First note down dz square. You write dz square is a combination of those two orbitals. You also note down those two orbitals. I am writing the h by 2 pi orbital angular momentum. For dz square it is 0. For d x square minus y square it is either plus 2 or minus 2. Plus or minus 2, if plus 2 is given for x square minus y square, for xy you give minus 2. If you give minus 2 for this, you give plus 2 for this. Later we have xz and yz. How do I draw xz? Why in detail I am giving these diagrams? Because understanding the orientation of d orbitals is important. This is inorganic. We will be having d block elements and transition metal complexes. So which orbital is this? The lobes are present between x and z. So this is dxz. H by 2 pi orbital angular momentum value is plus or minus 1. And lastly we are left out with dyz. So every orbital you have to imagine, and how should you imagine? Yesterday I told you, just for a minute you watch and then you can draw. Before you, supposing that this is z, x and y, these are the three coordinates, xz plane, yz plane, xy plane, 3 planes and 3 coordinates. Just imagine a plus before you, that is x square minus y square. Imagine a multiplication symbol, that is dxy. Multiplication symbol in this way, dxz. This is dyz. Plus symbol, dz square minus y square, dz square minus x square. So now did you get the difference? If I show it like this, it is dxz. This is dz square minus x square. There is a difference. So you should not imagine like this. This is xz, yz. This is z square minus y square, and two lobes above and below dz square. Okay, now you draw it. If anyone has completed this, I'll just ask a question. There is a question. First you complete it. In xz, two lobes are projecting towards you, two lobes are away from you. Those who have completed, note the question. Draw the shape of dx square plus y square orbital. Draw the shape of dx square plus y square orbital. Dx square plus y square. Completed? Okay, just before you draw, I'm just showing the coordinates so that you can visualize and then you can remember it easily. Imagine that this is plus coordinate, green, white is a minus coordinate. This is plus x, plus y, plus z and minus z. So these are the three coordinates. I join any of these two coordinates, that will give a plane. So if I just pass this plane, it is which plane? xz, yz, again yz. If I show it like this or if I show it like this, it is just one and the same. It is in the plane of the board. Plane of the board. Okay. This one xz, xz. Either I show it like this or like this, it is just one and the same. XY plane. Okay. So now within these three coordinates, we have d orbitals, plus plus minus minus. So if you are able to imagine the four lobes like this, within these three spatial coordinates, this is dx square minus y square. Okay. This is dxy. Dx square minus y square, this is dxy. Are you able to imagine dx square minus y square lobe? In between you have dxy. So how much is the angle between them? 45 degree. From here to here is 90 degree. In between you have xy lobes. So it is like 45 degree away. Okay. Next. This is which orbital? D xz. This is dxz or zx, anything. This is dxz. This is dyz. So when I hold dxz, two lobes are pointing towards you, two lobes are away from you. Okay, so whenever we draw it, we show two lobes towards you, two lobes are away from you. The two lobes pointing towards you are plus and minus. Away from you are also plus and minus, okay, yz. It is just like a perfect square. But whenever we draw xz, usually these two lobes we draw little larger because these are towards you. The lobes away from you we draw little smaller. Okay. Suppose if I show it like this, or maybe I'll show it like this. This is dz square minus x square. This is dxz. This is dz square minus x square. Dz square minus y square. Dyz. This is dyz. Okay. But for time being you just forget dz square minus x square. But in symmetry and group theory you will be getting different types of orbitals, d-orbitals. So it is not like only these 5 are fixed. No. X square comma y square comma z square, any linear combination of that will have the same symmetry as that of the corresponding IR. That is what we say in symmetry. So x square comma y square comma z square, when I take the linear combinations, which orbitals do I get? I can get z square minus x square, z square minus y square, I can get z square, I can get x square minus y square. Any combination is possible. Are you able to understand? Okay. Now on this ground I asked you a question, what is x square plus y square? How do you draw it? You never heard about x square plus y square. Always we heard about x square minus y square. What is x square minus y square? It means there is a nodal plane. That is the meaning. X square minus y square means there is a nodal plane in between. That is why you say x square minus y square. Electron density is present along this axis and this is not continued, it is discontinued into coming to y. So we say x square minus y square, we put only lobe. I am not continuing the electron density, I am just restricting the electron density to a lobe. There is no electron density, again a lobe, no electron density. Understood? But suppose if that electron density, imagine this is xy. Just for your convenience I am showing it like this, but this is xy plane. That electron density which is present in plus phase is now completely continued, totally continuing as an electron density. That is your dx square plus y square. Are you getting it? So this is like plus, 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 plus. If everything is plus, is there any node? No. So it is like a continuity. Then how should you imagine dx square plus y square? It is just like a circle. Not just a circle but electron density. That electron density is present all around x and y axis. Are you able to imagine now? If you are breaking it with nodes, two nodes, it is dx square minus y square. But for dx square plus y square there are no nodes. It is a continuity. Okay? Are you able to imagine that same circle in this direction? What is this? This is dz square plus x square, dz square plus y square, dx square plus y square. Okay? These things will come in group theory. When we go to symmetry and group theory, there you will be getting dx square plus y square. All things are possible. I will be just drawing dx square plus y square. This is dx square plus y square. Everywhere it is like plus only. So you have to put the electron density along x and y, and there is no breakage. Everywhere it is like plus only. This is dx square plus y square. Can I draw dx square plus z square or dz square plus z square plus x square? Z square plus x square. How should I draw it? Just try to imagine that it is in this plane. Okay, dz square plus x square. And how to draw dz square? Plus y square so you are drawing it like a perfect circle. If it is like elliptical, you are watching in this direction, elliptical in this direction, but like a circle in this direction. How you draw, based on that your imagination also depends. I'll just give a small example while you draw this. Suppose if I draw benzene like this, and I'm drawing benzene like this. So in which plane is this benzene? This benzene is in YZ plane. The same benzene, if I draw it like this, it is like in XY plane. So whenever I draw it in XY plane, this electron density, we don't put it like a circle. It will not be like a perfect symmetry. It should be like extended in this direction. Then I imagine, okay, this is along XY plane. Okay, so that is the difference. If I draw it like this or if I draw it like this, you have to imagine that I'm drawing in this plane YZ. I'm drawing in XY plane. Suppose if I draw it in XZ plane, this is XZ plane. So I draw the same benzene like this. I'm correct in all the three senses. I'm correct, but I'm orienting in a different plane. This benzene is in YZ plane, XZ plane, XY plane. So all these imaginations, they have to be in your brain. Okay, we don't draw f orbitals because they have too many lobes, so we cannot draw on board or on paper. So we simply skip it. We always restrict up to D orbital. Shall we conclude? I'm just concluding now. What are the various orbitals that we have, and the shapes anyway you are aware of. So I'm just taking S, P, D, and let me take F. Inversion, present, absent, present, absent. Parity, even, odd, even, odd. And symbol, gerede, ungerede, gerede, ungerede. There could be a hypothetical question, because in CSIR there is no restriction or limitation. There can be hypothetical questions also. Following that hypothetical question, I am giving you two more orbitals. Suppose we have G and H orbital. G and H. Simply these things will alternate. These things will alternate. So you have to just alternate the things, that's it. SPDF, later on you can have GHIJ. Even for GHIJ, all things are alternated. Inversion, present absent, present absent. If inversion is present, parity is even. If inversion is absent, parity is odd. And if it is even, the symbol given is gerede. If it is odd, the symbol given is ungerede. You just alternate them, that's it. Completed. I'll just give you one more energy level that we'll discuss in the electronic spectroscopy, not here, but just for a correlation. If I'm giving an orbital, This is atomic orbital S, P, D and F. You will be knowing full details in electronic spectroscopy. Can you look at the correlation? This is a correlation table which I have clubbing from different energy levels. If I am taking an orbital, is orbital an energy level? Is orbital an energy level? Yes. Orbit is an energy level, orbital is an energy level, everything is a energy level. If I take an atomic term, what is generally a term? It is another energy level which defines a specific configuration, that is called as atomic term. And what are the symbols given for atomic term? They are in capitals, capital S, P, D, F. So by mistake, and if you are writing capitals for an orbital, it will be wrong. Okay. Later on, let me move to a molecular orbital. What are the various molecular orbitals that we have? From the basic, we start from sigma, pi, delta, phi. Even for those molecular orbitals, there are some other energy levels to define where the electron is present. That is called as molecular terms. They are called as molecular terms. And those molecular terms, we write it in capital letters. Capital sigma, capital pi, capital delta, capital phi. Okay, simply have to put it in capitals. Now what correlation can you find in all these four? What is that correlation which is present in all these four? One is atomic term, molecular term, atomic orbital, molecular orbital. What is common in all these things? The accent. Suppose if I am starting from S-orbital, what is the accent or what is the pronunciation that I start from? Sir. Sir, S-orbital, S, Sir, sigma, S term or sigma, anything is starting from Sir. And for P-orbital, P. All the four are P. And for D-orbital, D. All the four are correlated with D. And the last one, F. So let it be atomic orbital, let it be molecular orbital, let it be atomic or molecular terms, the same pronunciation will continue. They'll change the symbol, but pronunciation remain the same. S, P, D, F. You just note down that correlation. And tomorrow I'll be starting with periodic table. Okay, periodic table, there are a few units which are completely basic units. So I'll be taking just like a gist of periodic table. Each and every point we need not give. Periodic table is known for you. But since we have D block elements and other block elements and transition elements and so on, you should have a basic idea about periodic table. So all important points of periodic table tomorrow I'll discuss. And tomorrow I'll take the complete session. Okay, the complete session I'll be taking so that I can have a rhythm. I'll continue with the periodic table right from the beginning till the end. Okay, what are the interesting facts starting from the periodic table? All those things I'll put forward. Finished? Okay, tomorrow we will be discussing periodic table, but let me ask you a small question. Law of octaves was given by? Not Manleve. Newlands. John Newlands has given law of octaves. What is the basis for law of octaves? Yeah, what did he take as the base? First element and eighth element are repetitive. They are having like repetitive characters. But what is the base for 1 and 8? Why 1 and 8? Why not 1 and 4? What note? Sorry? Which note? Who is saying it? Raise your hand, no problem. Because he did not take 1/4, 1/5, 1/6, 1/7. He has taken 1 and 8th. First and 8th. So on what basis did he say? Sa, Re, Ga, Ma, Pa, Da, Ne. 7. Again 8th note will be the repetitive of the first. But my simple question is, who gave this law? Newlands. Newland, was he a Telangana or Indian? No. Then how did he know Saregama Padanissa? Is it valid question or not? How did he know Saregama Padanissa? Now that is a real question, right? Did he come to India? No. But how was Mendeleev connected to India? He has given Eka boron, but it is not Eka boron, it is Eka. Eka means 1. 1 after the boron will be so and so. Or Eka aluminium, 1 after aluminium will be so and so. He has left some space for it. If at all another element will be discovered, you have to put it just below this. So he has kept some spaces also. Okay. He was interested in Sanskrit. So he has taken 3 words, Eka, Dvi and 3. But we are only aware of Eka. Because 3 and 3 generally it is not given in our textbooks. So we are only confined with Eka, but it is from Sanskrit, Eka, not Eka boron, not Eka aluminum. It is not Eka, it is Eka. But how is Newland related to India? Then we say it is not Saregama Padani what he followed. It was Do Re Mi Fa Solati. So after Do Re Mi Fa Solati, again Do will be repeating. Based on that he has taken it. Okay. Anyway, all that is history. Now let us come to the notes. This everyone is aware of notes. So I am not going to discuss much. How many notes are present for S orbital? 0? 0? It is like everywhere plus. Everywhere it is like plus phase only. So is there any phase difference? No. No phase difference. So the number of nodes are 0. But when I say the number of nodes, what type of node is it? All these things will be dealt in quantum chemistry. Here I am just giving an introduction only. Details will be coming in your quantum chemistry physical. Here just one point I am giving for each node or each orbital. When we speak about the nodes, we have angular nodes as well as radial nodes. Angular node is different from radial node. Angular node is with respect to that particular orbital only. Okay, it is like in organic chemistry we will be studying intramolecular and intermolecular. Intramolecular within the, inter in between. So suppose if there is any node within the orbital, it is angular node. And if there is any node or a phase difference or a sign difference in between the orbitals, that is radial node. Okay, I am putting it very simply. So if at all there is any node within the orbital, it is angular. In between the orbitals, it is radial. Which orbitals in between means? In between identical orbitals. Don't compare between S and P. Compare between 1s and 2s, 2s and 3s, or 1s and 3s, and so on. Okay, note down. There are 2 types of nodes. There are 2 types of nodes. One angular, second radial node. First one angular node, second one radial node. Next point. Angular node is present Angular node is present within the orbital. Angular node is present within the orbital. Within the orbital. Next, radial node. Radial node is present between the identical orbitals. Between the identical orbitals. Identical orbitals. So how should you imagine? Just suppose if there is a nucleus, around this nucleus there is S electron density just like a sphere or like a completely ball, and that complete ball, if it is in plus phase, if that complete ball is in plus phase, 2s orbital will be in minus phase. 2s has to be minus. Then I move to 3s, 3s has to be plus. I move to 4s, it has to be minus. So always there will be a phase difference between the identical orbitals. It will continue for each and every orbital. Even if I take p orbital, in p orbital, suppose if this is 2p orbital, plus and minus. After this we have 3p. In the p I am saying 2p, after 2p we have 3p, but for 3p this is how the lobes will be. Are you able to imagine pz? In that pz, imagine this is plus, this is minus. And if I am going for 3p, 3p will not be like this. It will be larger, but it will be like this. Minus and plus. If I go for 4p, again plus and minus. So minus plus, plus and minus, they continue. There is a phase difference, and that is creating a node. That node is a radial node. So for 1s, is there any other orbital before? No. It is directly from the nucleus. So there is no other phase difference. So for 1s orbital there is no radial node. But look at for 2s orbital. For 2s, is there a phase difference? Yes. 1s is yellow in the sense plus. 2s is blue. There is a nodal plane in between, or a nodal point in between, or nodal space in between. I cannot call it as a nodal plane. I can call it as a nodal space. Okay, between 1s and 2s there is a nodal space. Between 2s and 3s there is a nodal space, and it has to change the phase also. So all 1s if it is plus, all 1s if it is plus, 2s has to be minus completely, 3s has to be plus, and so on. You can note it. So how many radial nodes for 3s? For 3s how many radial nodes? 1, 2. For 2s how many radial nodes? For 1s 0. Likewise for p orbitals also we can write. For p orbitals, but we don't draw. There are 3 p orbitals. It will become difficult for me to draw. I can just show it for only one orbital. For p orbital how many angular nodes? For p orbital I am only considering one p orbital, okay? I am just considering one p orbital only. Say this is 2p orbital. So if I can give this, this will be 2p, 2p. Now can you see a nodal plane? I am just trying to show the nodal plane. This is a nodal plane or a nodal point anything you can call it as. So between this p orbital and this p orbital there is one node, nodal space, a second space. So if I go for 4p has how many radial nodes? 4p has 1, 2. Center is the nucleus. This has 2 radial nodes. 3p has 1. 2p has 0. Angular nodes, how many angular nodes? Angular nodes, 1 angular node. Okay. So likewise for d orbital, if I take for d orbital, center will be the nucleus. How many nodal planes for a d orbital? How many nodal planes? This is plus minus plus minus plus minus. So how many angular nodes? 2. There will be 2 angular nodes. And if I want to put the radial nodes, again you have to alternate. So imagine if this is plus plus, this is minus minus, this is of 3D, then 4D will be plus plus minus minus, this will be 4D. This will be 5D. Are you getting the point? Did you get the point? Radial nodes. Radial node means it is a nodal plane or a nodal point or a nodal space present between the orbitals, between the identical orbitals. So between 3D and 4D there is one nodal space. Okay, between 4D and 5D there are 2 means one nodal space. So between 3D and 5D, 2 nodal spaces. Okay, so there is one nodal space between 3D and 4D, 4D and 5D another nodal space, 3D and 5D, you just go on counting it. There is a simple formula. Can anyone tell me the formula? Because every time calculating all these things, this is only explanation part, but in the exam you just can't go drawing and how many nodal spaces are present in between. It is very difficult. What is the formula, simplest formula that you can give? 0, 0, 1. Okay, I'm giving it. You note it. First of all, I'm giving angular nodes. Zero, 1, 2, 3. These are angular nodes, not radial nodes. SP, DF, you can also correlate them to molecular orbital. Suppose if you want to correlate to molecular orbital, even they will have same number of nodes. You can correlate, no problem. Sigma molecular orbital will have 0 nodes. Pi molecular orbital will have 1 node. Definitely there will be a node. Sigma bond, how is it formed? Head-to-head overlap. Electron density is present around the internuclear axis. But in pi bond, it is present perpendicular to the internuclear axis. Electron density is present perpendicular to the internuclear axis. There you will get a node. Even for molecular orbitals sigma pi delta phi, the number of angular nodes are same as the corresponding atomic orbitals. Now a small question, right? How many nodes are present? Write the question. How many nodes are present? How many nodes are present for delta star molecular orbital? How many nodes are present for delta star molecular orbital? What is your answer? How many? Delta star is 1. The simplest way to remember is how many nodes are there for the bonding molecular orbital. One node will increase for antibonding molecular orbital. I said delta star. Delta star means antibonding. So how many nodes are there for delta? Delta star should be 3. Just increase one more. How many nodes for sigma molecular orbital? 0. Sigma star 1. Pi 1. Pi star 2. Delta 2. Delta star 3. Phi star will be 4. Okay. So that will continue. Suppose if gamma bond is present, gamma molecular orbital is there. G atomic orbital. G gamma, suppose. How many nodes? 4. And star 5. So we just increase one node for corresponding atomic orbitals or molecular orbitals. Increase one more node for antibonding molecular orbitals. Okay, simple. Radial nodes, don't take n-1, n-2, n-3. I'll just ask a question. If it is in concurrence with that, you can note it. 2s atomic orbital, how many radial nodes? 2s, how many radial nodes? 1. 5s. So suppose if I give you ns, so for any s orbital, n-1 will give you the number of radial nodes. P orbital will begin from which shell? It will begin from L shell. It will not start from first shell, it will start from the second shell. So 2p will not have any radial node. 2s will have one. 2p? No. 3p? Again 4p? 2. 5p? So every time it is like -2, -2. 2p? Nothing. 3p? 1. 4p? 2. So it is like n minus 2. Directly if I ask you for 5p orbital, how many radial nodes? Completed. Likewise D will begin from 3d. So till 3 there is no radial node, so make it n minus 3. F orbital will start from 4th shell. So till 4 there is no radial node, go with n minus 4. Okay. N minus 1, n minus 2, n minus 3, n minus 4 for SPDF radial nodes. Angular nodes, accordingly you can add. S orbital has anyway 0, P orbital has 1. That is fixed. Let it be 5p orbital, 6p orbital. Angular node is only 1 for p orbital. Let it be 6d orbital or 10d orbital. Angular nodes are only 2. Along with that you can add this. So in the exam they can ask you what are the total number of nodes. Total number means it is radial plus angular both. Or they may simply ask you angular. Or they may simply ask you radial. Anything. You can note it n minus 1. Completed? Write a question. What is the formula? What is the formula to find out what is the formula to find out the total number of nodes? Anyone? Directly there is a formula to find out the total number of nodes. How much? If you don't answer today, tomorrow you have to answer. I will not give it. At least one should be for your assignment. If anyone can answer, that is fine. We'll take it for discussion. Otherwise, tomorrow you have to get it. No? Okay, now let us move for bonds. Tomorrow, you just tell me the formula. It is a very simple formula. You just tell me that formula and you need not count n minus 1 plus 0, n minus 2 plus 1. All those things you need not do. There is a simple formula. N minus. You have to include a quantum number into that formula. There are two quantum numbers in that formula. Anyone? Okay, you try to get it, no problem. Till tomorrow also you need not wait. Just whenever I give a break, in that break also you can get the formula. Let us move to the last step. Write down. Bonds. Bonds. Different types of bonds. Different types of bonds. Different types of bonds and their combinations. Different types of bonds and their combinations. First one, sigma bond. Sigma bond, just 1 or 2 points. It is formed due to or from head-to-head overlap, or what is the other name? Linear overlap. Head-to-head overlap or linear overlap. Second important point, only those orbitals combine to give a sigma bond which have h by 2 pi orbital angular momentum value of 0. It has to be 0. So what are the various combinations? Let me write the combinations. First of all, h by 2 pi 0 value orbitals S, Pz and dz square. Only these orbitals can give you sigma. So now let me write the combinations. S plus S, S plus Pz, S plus dz square, Pz plus Pz, Pz plus dz square and dz square plus dz square. All these combinations can give you sigma bond. Along with this, hybrid orbitals sp, sp2, sp3, they will also give you sigma. I am not including. If you want, you can just include. It is a organic part. Along with that, even sp, sp2, sp3 hybrid orbitals can also form sigma bonds. Let me just take one combination. Or else I'll give you can note down the combinations of sigma. So where are the nuclei present? They are present in the center. And these are the two nuclei. These are the two nuclei. How antibonding molecular orbital is different from a bonding molecular orbital? How is it different? Simply from the diagrams also you can see between the nuclei, in the atomic orbitals between the nuclei, the electron density is comparatively low. But in a bonding molecular orbital, the electron density between the two nuclei increase. And whenever electron density between the two nuclei increase, that is BMO. Whenever the electron density between the two nuclei decrease, that is ABMO. So for ABMO, can you see the nuclei? They are very close. Between the nuclei, electron density should be low. Therefore, electron density will move away from the nuclei. You should not draw nuclei in the center for ABMO. Okay? It has to be like towards the edge. Both nuclei are coming close and electron density is moving away from one another. You look at the phase, plus and minus. Okay, but for BMO, everywhere it will be like plus only. Okay, do you find any nodal plane? For sigma BMO, is there any nodal plane? No, everywhere it is like plus. There is no phase difference. But in ABMO, there is a nodal plane. So just previously I told you, for any bonding, if the number of nodes are 0, for antibonding you have to add plus 1. Always plus 1. You can just draw it. We are not concerned about sigma ABMO. We are concerned about sigma BMO because we are talking about sigma bond. For sigma bond, consider BMO. Don't consider ABMO. What is LCAO? Linear combination of atomic orbitals. What is SALC? We either call it as LCAO or we can also call it as SALC. SALC means, write down. First write LCAO. LCAO means linear combination of atomic orbitals. What type of method is it? LCAO, what type of method is it? It is an approximation method. Okay, it is an approximation method. LCAO means linear combination of atomic orbitals. And always remember, whenever I say linear combination, either they can add or they can subtract. Linear means that is the meaning. Either they add or they subtract. Both things can happen. Whenever they add, you get bonding. Whenever they subtract, you get antibonding. Next, SALC. SALC, symmetry adopted linear combination. Symmetry adopted linear combination. Now, from your quantum chemistry point of view, I'm not a physical chemistry lecturer right now, right? My simple question is, how will you explain a BMO and an ABMO with respect to a simple mathematical equation? How do you explain a BMO with respect to ABMO? How will you compare them with respect to a simple mathematical equation or a simple mathematical formula? Half NB minus NA. That is for bond order. Yeah, that is bond order. Bond order is half of bonding electrons minus antibonding electron. That is bond order. But my question is not exactly for bond order. How do you compare BMO with ABMO with respect to a simple mathematical formula? I take the electron density of one s atomic orbital. There are two s atomic orbitals which are combining. One I am taking it as a square. One I am taking it as b square. So how can they combine? Or instead of saying a square b square, it is like a and b. So how can they combine a plus b whole square, a minus b whole square? A plus b whole square will give you BMO, A minus B whole square will give you ABMO. So A plus B whole square, what is the formula? What is the formula for A plus B whole square? I think I am asking you very basics of math. A plus B, A minus B. This is A square. In this case, A square or B square is the electron density of pure atomic orbital. A square and B square is as it is there. Okay, it is even continued in this. But along with that A square and B square, there is an increased electron density by 2 AB units. A square B square is already there. It is from atomic orbitals. But along with that, how much electron density has increased? 2 AB electron density has increased. For this, A square plus B square is already there, but it is losing some electron density by 2 AB units. So whatever this is gaining, the same is lost by this. In between, don't put that electron density related to 2 AB units. That same electron density will be found between these two. Okay? If you want to just write down this formula. A plus B whole square to define BMO. A minus B whole square to define ABMO. Sideway overlap. Orbitals. With h by 2 pi orbital angular momentum of plus or minus 1. So what are those orbitals? We have px, we have py, dxz, dyz. Any combination of these. And when I say any combination of these, it is symmetry allowed combination. Remember, symmetry allowed combination means, can I take px and py? Px is like towards you and away from you. Py is this, towards your right and left. Can they combine for sideway overlap? Not possible. That is why we say SALC. SALC means symmetry adapted linear combination. If these lobes are in x direction, these two lobes also should be in x direction. That is the meaning of SALC. So Px can only combine with Px. Py can only combine with Py. Px can combine with dxz. X and x common. Py can combine with dyz. Y and y common. Dxz can combine with dxz. And dyz can combine with dyz. Only these are the possibilities. Either I can draw it like this, or I can also draw it like this. This is the internuclear axis. Electron density is not present in the internuclear axis. It is distributed above or below. So you call it as sideway overlap. It is not head-to-head overlap. Do you find any nodal plane in BMO? Do you find any nodal plane? Yes, there is a nodal plane. One nodal plane is present. In this case, 1, 2. So the nodal planes are increasing by 1. between bonding and antibonding. And while drawing antibonding orbitals, please look the diagram. How did I draw the lobes? They have to move away. But for bonding, straight. Either you put straight or you join them, combine them. But for antibonding, they should go away from one another, from the nucleus. So above you can see plus minus, below also you can see plus minus. Let me ask you a small question. In sigma BMO, do you have inversion? Look at this sigma BMO. Do you have inversion? Yes. From the center, if you draw a line meeting plus in one direction, opposite also plus. Sigma ABMO? No, one side if it is plus, the other side will be minus. So inversion, sigma BMO, ABMO, absent. Come for pi. Pi BMO, do you have inversion? Starting from the center, if I draw a line meeting plus in the opposite direction meeting, inversion is absent. But in this case, starting from the center, meeting plus, opposite also meeting plus, meeting minus, opposite also meeting minus, inversion is present. It will be present. Again it will alternate. That will be a very important point when you go to chemical bonding. In chemical bonding, we give two important points or guidelines. Sigma BMO and pi ABMO are gerede. Sigma ABMO and pi BMO are ungerede. Sigma BMO and pi ABMO are gerede. Sigma ABMO and pi BMO are ungerede. Two important statements which you will come across in chemical bonding also. So how many lobes are overlapping from each orbital? Only two lobes. Whatever be the orbital. Suppose if I am taking dxz combining with another dxz, these will combine. So only two lobes of each orbital are combining. Not like this. I am not that better artist. Just imagine that you are looking from this side or maybe from this side. Okay? When you are looking from this side, how many lobes are you able to see? Only two lobes. Actually there are 8 lobes in this plane. Okay, just imagine those 8 lobes are now in this plane. When you are looking from this point, how many lobes can you see? Only plus and minus, only 2 lobes. Between those 2 lobes, how many nodes are present? Only one node. So let it be dxz or dxz, let it be dyz or yz, px or px, py or py, you will have only one node. Whatever may be the combination. And all these combinations will be like only 2 lobes when you are looking from the side. When you are looking from the side. Okay. Now let me give you in the symmetry point of view. In the symmetry, if I take a ball having all plus and I am trying to pass a rotational axis, by what angle when I move there is a phase difference. Plus and minus has to change. There is a ball. By what angle when I move I get a phase difference? No. Everywhere it is like plus only. Therefore we say 0 node. Node is 0. But if I take any p combination or any dxz dyz combination, there will be like 2 lobes, plus above minus below. And as I rotate, at least once you will get a phase difference. Plus and minus. When I rotate by 360 degree, before I rotate to 360, I am getting one time plus and minus. This is plus and this is minus. Therefore we say there is one node. Did you get my point? If you do the same for a d orbital dx square minus y square rotation, 2 times they repeat. Therefore we say 2 nodes. That is at a higher level. But the simpler level is, can I pass a node? There is only one node. Okay. Last one, delta bond. Last one, delta bond. Delta bond is eclipsed overlap. And which orbitals combine? Orbitals with h by 2 pi orbital angular momentum of plus or minus 2, and the combinations of plus or minus 2 are only two. One is dx square minus y square and dxy. So what are the various combinations for delta bond? X square minus y square plus x square minus y square, dxy plus dxy. These basics will help you in the metal clusters also. When we go to metal clusters, you will have sigma, pi, pi, delta. These are the combinations there. Only d orbitals are involved. No s, no p. So the same things will repeat. These combinations are symmetry forbidden. Only the above combinations are symmetry allowed. These two lobes overlap. These two lobes overlap, these two lobes overlap, these two lobes overlap. It means all four lobes of one orbital will overlap with all four lobes of other orbital. It is like eclipsed overlap. Okay, that is delta. White, imagine that they are towards you and away from you. Yellow, above and below. I'll just show you the combination, then you can draw. Suppose if this is 1 dx square minus y square, this is dx square minus y square, this is another dx square minus y square. For your convenience, I am showing it like this. So 1 lobe, 2 lobes, 3 lobes, 4 lobes. All the above 4 lobes, all the below 4 lobes, they try to overlap. It is a very weak overlap. Okay, this is delta. Or I can also draw it like this. This is delta. Okay. Pi bond, sigma. So head to head overlap or linear overlap, sigma. Sideway overlap, only 2 lobes of each orbital will participate. And delta, eclipsed overlap. Okay. In this linear overlap, they can come much closer. They can come much closer. But in sideway overlap, they cannot come much closer. What is happening, can you see? If I am just holding it like this, if imagine this is the nucleus and this is the nucleus, they are far apart. Even if I overlap up till this distance, can you see the distance between the two nuclei? Overlap is very strong, almost bond to bond overlap. Still the nuclei are distant. But just look at the pi bond. Already the distance is close between the nuclei. As they try to overlap, the nuclei are coming close. They start repelling. Since they start repelling, overlap will not be that efficient. It will be less efficient. That is why we always say pi bond is less stronger than sigma. Delta is still less stronger because it is very much weaker. Now, just let me show the delta bond like this. These two are overlapping. In this overlap, forget about the internuclear axis. How many nodes are present? 1, 2. Can you see 1 node, 2 node? Okay. Between these two, do you have any node? Between these two, do you have any node? No. There is no node. But suppose if they combine like this, if they combine like this, now how many nodes? 1 and 2 are there. There is also a third one. This is delta star. This is delta star. In delta star they move away from one another. If this is plus, this will be minus. Okay, if this is minus, this will be plus. So they move away. There is one more nodal plane. So 1, 2 and 3. Delta star. Delta. Only 2 nodal planes. Pi. Only 1 nodal plane. Pi star. 2 nodal planes. Sigma. 0 nodal plane. Sigma star. 1 nodal plane. Okay. So this completes all the different types of bonds that we are going to come across. Sigma, pi and delta. For sigma there are more number of combinations. For pi at least 6 combinations are there. For sigma 6 plus sp, sp2, sp3. So you can call it as 9 combinations. And for delta only 2 combinations. Dx square minus y square plus dx square minus y square. Dxy plus dxy, but not the other way. Okay. And the most important point to remember, h by 2 pi orbital angular momentum values. If it is 0, sigma bond. If it is 1, they can form a pi bond. And if it is 2, they can form a delta bond. Suppose if it is 3, phi bond. Yesterday we have discussed single, double, triple, quadruple, quintuple and sextuple. In sextuple there is a 1 phi bond. There is 1 phi bond. There is delta, 2 pi and 1 sigma. But we have to go up to quadruple bond only. Okay. In quadruple bond, how many sigma? 1 sigma. How many pi? 2 pi. And how many delta? 1 delta. Okay. Right. Last question. I think you have answered it. How many nodes are present in d x square plus y square orbital? How many nodes are present in dx square plus y square orbital? Answer? I am asking about angular only because I did not mention the quantum number. Had I mentioned 4d, 5d, then you should have thought about radial nodes. I just gave you dx square plus y square, means it is angular only. How many angular nodes? 0. Because everywhere it is like same phase. Everywhere it is like same phase. Therefore the number of nodes in dx square plus y square is 0. One last general knowledge question. Principal quantum number, how are they numbered? 1, 2, 3, 4. But what alphabets are given for it? Why not ABCD? K means kernel. Yesterday I told you SPDF. Why didn't they choose ABCD? SPDF, sharp, principal, diffuse and fundamentals from the spectral lines. Here again they did not choose ABCD. They started from KLMN. K means core or the kernel. Whichever is the central part, we call it as a core. In English we generally start from C. But when you go to Greek and Latin, generally they start from K. Kernel or core is K. It is much closer to the nucleus. Since the very first shell is much closer to the nucleus, it is like core shell. Therefore they started from plus. They started from 1. Later on alphabetical order, K, L, M, N and so on. Okay, right. So tomorrow again I am repeating, periodic table will be done tomorrow. Okay.